Physics Unit 1, homework book, page 14, and we're now talking about diffraction and diffraction gratings. And we've just got a little definition for diffraction, and we've got little helpful diagrams here of aerial views of the seashore. And this is where the waves spread out in kind of circular fashion. So spreading of the waves as they pass through this gap here, and we're going to give this gap a name called the aperture. So spreading of waves as they pass through an aperture or a gap, and the size of this gap will influence our waves. So I'm going to just draw some waves in these three questions here, kind of similar distance apart. So our wavelengths, as you can see there, are the same for all of these three questions. So our wavelength is lambda there, and you can see the wavelength is the same for those. For the first one, we've got the aperture the same width. The aperture width is the same as the wavelength. So that's my aperture there. And what happens is the wavelength doesn't change, but you get diffraction. If I make this aperture absolutely massive, so massive gap, massive aperture, then these waves really just go straight through. So they largely go through unchanged, but actually just bend around just at the sides a bit, where they've been influenced by the barrier there. So that's the aperture is larger than the wavelength. And the kind of final situation, if we make this aperture teeny tiny, so my aperture is still there but very, very small, then these waves will actually get reflected. So let's draw a kind of dotted line to show that these will be reflected. Again, still with the same wavelength, so we've got reflection there. So the wavelength never changes. So if you draw these in an exam, the wavelength never changes, but it might be diffracted or it might be reflected. Then we've got a bit of theory on the next page, and Young's double slits experiment. Hopefully you've watched the video on this. The video is much better than any picture can show you. And this goes back to our constructive and destructive interference. Our lines on here are our dotted line is like the peak of a wave, so we've got the crest, and our solid line is like the trough. And so where a peak meets a peak, we get a super peak, and where a trough meets a trough, we get a super trough. But where we get the two different things joining together, then we get them cancelling out. So where a peak meets a trough, that's destructive interference, and if it was on water, it'd be quite calm. Why are we interested in this context? Well, light is actually also a wave, and we can use these kind of emission spectra and diffraction gratings to investigate stars by looking at the light and seeing the interference patterns of these waves. So that's why we're interested. You looked through a little slide thing, or a little telescope looking thing. That was a diffraction grating, and a diffraction grating has apertures in it. So you've got the gap that you had for diffraction, like on these diagrams here, but on your little slide they looked through, they were so small you could hardly see them, but they are little gaps for the light to go through. So the question is, why do you think red, orange and blue light diffract by different amounts? Well, you've noticed the diffraction here, it can be influenced by the aperture, but actually this wavelength compared to the aperture would influence the diffraction. So this wavelength, and we know that in different parts of the light spectrum we've got different wavelengths. So that's the main reason there. So they have different wavelengths, and I'll put a little lambda there. So for example, red has a longer wavelength, so diffracts more. And why are we interested? So we can find out what stars are made of by looking at the light. So we can find out what stars are made of using their emission spectra. So for example, each element would give off different, a different unique spectrum. So each element gives a unique spectrum, and you can compare that to the spectra given by elements that you know on Earth. So you can create these and then compare them to the light that you're getting from stars, and you can work out all sorts of things. The age of the star, how far along the star cycle it is, that sort of thing. Can compare with known spectra from elements on Earth. And you looked at some in the lab using various, I think we had some noble gases, we had some neon lights, and we looked at those through the gratings, and you could see the differences there. I'll do the next set of questions in the next video.